So the next thing we're going to take a look at are secant lines versus tangent lines, and rates of change, and kind of getting into how we can find derivatives numerically, what derivatives mean, what a secant line means, what a tangent line means, all that stuff. So here's what we're trying to do. Let's say I have a function, f of x, and I have a particular x value a. My goal is to try to find the derivative of my function at x equals a. I want to try to find the slope of the line tangent to f of x at x equals a. I want to find that slope. Problem is that's too hard for right now. We don't actually know how to find the slope given just a single point. You need 2 points to be able to find the slope. So we're going to kind of hold off on that question for right now, the slope just at a single point. And instead, rather than focusing on tangent lines, we're going to focus on what we call secant lines. A secant line, and hopefully you remember this definition from geometry. If not, well, here it is. A secant line is a line through 2 points on a function. A secant line is a line through 2 points on a function. A secant line is a line through 2 points on a function. So for example, I've got a point over here, I've got another point over here. A secant line might look like this. And I guess the point is that the slope of the secant line is not the same as the slope of the tangent line, but it's not a terrible approximation. I think they're fairly similar, I guess. In word problems, the slope of a secant line gives us what we call an average rate of change between 2 points. In word problems, the slope of a secant line gives us an average rate of change between 2 points. In word problems, the slope of a secant line gives us an average rate of change between 2 points. And I think after you've copied that down, we're going to kind of pause from this part of the notes, and we're going to take a look at that worksheet titled Section 2.1, Secants, Tangents, and Rates of Change in Class Examples. If you need more time to copy, please push pause. But if you're set, I'd like to try to deal with some of these average rates of change. In problem number 1, we're told the number n of locations of a popular coffee house is given in the table. Those were the locations as of June 30th back in 1998, 99, and so on. Part A, I want to find the average rate of growth from 2000 to 2002, and I want to include units. Well, here's 2000. Here's 2002. All I'm going to do is kind of find the slope between these 2 points, or also find the change in the number of coffee houses over the change in time. I'm going to do 5,886 minus 3,501 over, I think it's time for a new pen, maybe this one will work, over 2002 minus 2,000. Go to the calculator, and let's figure out what this thing is. 5,886 minus 3,501 divided by 2,002 minus 2,000. Type that into the calculator. And we should be getting 1,192.5. I've got to figure out the units here. Actually, do you have any idea what the units might be? If I look at what's going on here, up top, this was the number of coffee houses. This is actually the difference in the number of coffee houses in the 2 years. Coffee houses minus coffee houses gives me something that's coffee houses. This is a year minus another year. My answer is going to be, well, the number of years between the two. Therefore, my units are going to be coffee houses per year. Between 2000 and 2002, the number of coffee houses grew at a rate of approximately 1,192.5 coffee houses per year. That's my average rate of change over that 2-year span. You go try letter B and make sure you put units on your answer. Okay, so this is going to be 4,709 minus 3,501 over 2,001 minus 2,000. And that's going to give me 1,208. And the units are the same as the last one. This is coffee houses per year. Go try letter C. 3,501 minus 2,135 over 2,000 minus 1999. I'm going to go to the calculator. 3,501 minus 2,135 divided by 1 gives me 1,366 coffee houses per year. So it looks like over the time interval from 1999 to 2000, the coffee houses were growing a little bit quicker than between 2000 and 2001, and also quicker than over 2000 to 2002. But what we've been finding is the slope of a secant line, really just the slope of any sort of line, y2 minus y1 over x2 minus x1, which is telling us the average rate of change. Next, let's take a look at problem number 2 on here. If a cylindrical tank holds 100,000 gallons of water, which can be drained from the bottom of the tank in an hour, then the volume of water remaining, remaining in the tank, after t minutes is given by this formula over here. In letter A, I want to find the average rate of water flow between t equals 10 and t equals 20, and I want to include units. Well, I need to find the change in the volume of water over the change in time. Or, using like slope ideas, v of 20 minus v of 10 over 20 minus 10. Now, what you're going to need to do is find v of 20 and v of 10. You're going to plug 20 in here, you're going to plug 10 in there. Let me show you a shortcut way we can do this on the calculator. Hopefully this will work. Yep, you can kind of see things there. I would like you to take a moment and store your function in the calculator in y1. Under y1, I'm going to type in 100,000 times 1 minus, I can't really use t, I'm going to use x, but that's fine, x over 60 in parentheses squared. Once it's in there, go back to the home screen, second quit, and remember, push pause if you need another moment. But then, If you push the variables button, vars, over here next to clear, go over to y variables, select function, because right now we're in function mode on the calculator rather than parametric or polar mode, and select y1. If I type in y1, parenthesis, 20, close the parentheses, the calculator will evaluate y1 at x equals 20. The calculator really just figured out v of 20 for us. Well, that's kind of nice, which means I don't actually have to go on the home screen and type in 100,000 times 1 minus 20 over 60 squared, and then 100,000 times 1 minus 10 over 60 squared, and all that stuff. I can just evaluate directly on the calculator. Actually, why don't I just do that entire problem of v of 20 minus v of 10? I'm going to push variables. I'm going to go over to y variables, function, y1. I'm going to say 20 again, minus variables, y variables, function, 10. I'm going to push enter, and then I'll divide by 10. And I just found that the average rate of water flow, okay, there's a lot I need to figure out here, is negative 2,500. First thing I want to deal with is, what are the units? What are the units over here? Well, let's see. The top was in, volume was measured in gallons. So gallons minus gallons gives me gallons. The time on the bottom was measured in minutes, so minutes minus minutes gives me minutes. This is gallons per minute. Is it okay that this is negative? What does that negative sign mean? Well, this is the rate of change of really the water flow, sorry. This is the rate of change of the water flow in the tank. It's negative. This just means the water is draining out of the tank. Perfectly okay for this thing to be negative there. Actually would make sense that it's negative because we're losing water from the tank. Next, I know now how to find the average rate of change over an interval between time 10 and between time 20, for example. But my ultimate goal is to find the instantaneous rate of water flow, not over an interval, not between time 10 and 20 or 10 and 11 or something like that, but right at one specific instant, right at exactly 10 minutes. What I actually want to find is not the slope of a secant line, but the slope of a tangent line. I actually want to write this in our notes. In word problems, the slope of a secant line gives us an average rate of change between 2 points. And in word problems, the slope of a tangent line, the derivative, gives us what we call an instantaneous rate of change at a single point. In word problems, the slope of a tangent line so-called the derivative, gives us an instantaneous rate of change. I don't want to find the rate that water is flowing out of the tank between time 10 and time 20. I want to find the instantaneous rate right at time 10 or right at time 13 or something like that. If you need another moment, pause there. But let's take a look at how we can do this. We still don't know how to actually find the derivative at a single point. But I want to deal with t equals 10. How about instead I find the average rate of change of the water in the tank between time 10 and time 11. V of 11 minus V of 10 over 11 minus 10. This is not right at 10, but it's between time 10 minutes and 11 minutes. That's not a bad approximation. Go to your calculator and see if you can get a number for this. Same way we've dealt with the other one. It's already stored in y1, so go to the calculator and see what happens. Okay, and make sure you're putting units on your answer. I'm going to do variables. Function y1 of 11 minus y1 of 10. Divide by 11 minus 10. Well, I know that it's 1, but just for fun, I'll type that in there. I'm getting negative 2,750. Between time 10 and 11, the average rate of change of the water in the tank, negative 2,750 gallons per minute. Okay. What if I looked at a smaller interval really close to time 10? What if I looked at between time 10 and time 10.1? Go find the average rate of change of the water in the tank at that time. Okay, so same calculation I've been doing. y1 of 10.1 minus y1 of 10. Oops. Because I didn't open the parentheses. Okay. Over 10.1 minus 10. I'm getting negative 2,775. And this is going to be, again, gallons per minute. What if I look at between time 10 and 10.001? It's really close to right at 10. It's a really, really small interval. It's going to be a pretty good approximation. Go do it. Okay, let's see here. y1 of 10.001 minus y1 of 10, oops, didn't need those parentheses, over 10 point, oops, and the parentheses there too, 10.001 minus 10, I'm getting about negative 2,777.75 gallons per minute. So this is over a really, really small interval. If instead of dealing with a small interval, I wanted to find it right at 10, would it seem reasonable, these are kind of leveling out and stuff, would it seem reasonable that the instantaneous rate of change at 10 would be just negative 2,777.7 repeating? If we did between like 10 and 10.00001 and kind of made the interval smaller and smaller and smaller and it continued, we would see that we would get negative 2,777.7 repeating. Don't worry too much about where I got that number. That's kind of where we're going anyhow in this chapter. But I'm going to say right at time 10, that's the rate of change of the amount of water in the tank. We need to see how to actually calculate this, though, without just using these approximations.